Welcome to this explainer. Today, we're taking a strategic growth journey right into the absolute foundation of digital trust. As leaders, you already know that data is, without a doubt, your most valuable asset. But how exactly do we protect it? Well, let's dive into it. We're going to turn some fairly abstract coding concepts into what looks like a visual magic trick. We'll trace the evolution of encryption, literally from ancient times all the way up to the foundational logic that drives modern Python code. Because when you actually understand these underlying mechanics, you are going to be in a much better position to guide your organization's security goals moving forward. To really grasp the strategic landscape here, we have to recognize that encryption is a profoundly powerful double-edged sword. Now, on the left side, you see the correct use. This is your defensive shield, right? It's what secures your company's passwords, safeguards your websites, and honestly, just protects our everyday WhatsApp messages from prying eyes. But look over at the right side. The exact same mathematical principles can be weaponized as ransomware. Malicious actors use this very same encryption to lock your files and demand a ransom to unlock them. As leaders, understanding this tool is step one in mitigating that massive risk. So here is our roadmap for today's briefing. We'll start with the art of hiding secrets, look at how computers read letters, check out a simple shift cipher, transition into ones and zeros, uncover the reversible XOR magic, and finally unlock the message. We are building this step by step from basic human logic to actual machine-level magic. Okay, section 1, the art of hiding secrets. Before we even look at the code securing our data, let's just make sure we have the fundamental vocabulary down. It all starts with something called plain text. In cryptography, plain text is simply your information in its original, perfectly readable form. This is your raw data, your strategic memos, customer records, financial reports, basically everything, right before any secret locks or mathematical scribbles get applied to it. Which brings us to the flip side, ciphertext. When we apply encryption, that highly readable plain text is scrambled into an unreadable form. It helps to think of ciphertext like a completely secure physical lockbox. Literally, no one can read or unlock the message inside that box unless they own the actual secret key. So how do we get our data from plain text into ciphertext? Well, there's been quite an evolution. Simple encryption uses fixed, really easy rules, like just shifting each letter by a certain number. That's famously known as the Caesar cipher. But obviously, in a modern enterprise landscape, simple just does not cut it anymore. And that is why we evolved to complex encryption. This uses heavy mathematical equations and incredibly long keys. Think of the AES algorithm, which is absolutely the gold standard used by banks and major tech companies today. Moving right along to section 2, how computers read letters. To execute that complex encryption securely at scale, we have to recognize a basic truth about our hardware. Here's the thing, computers don't actually understand letters at all. They only understand numbers. So how do we encrypt text? Well, we use a couple of magic tools in Python to bridge that gap. Notice these two absolutely vital functions. First, we have the ORD function. This takes a character, let's say the capital letter A, and instantly converts it into its corresponding Unicode number, which happens to be 65. Then we have the Crower function, which perfectly reverses it, taking that 65 and converting it right back into the letter A. This translation phase is literally the bedrock of digital cryptography. All right, section 3, the simple shift cipher. Let's look at our level 1 encryption to see how shifting these numbers actually hides message. The logic behind a Caesar cipher is beautifully straightforward. It's just 3 steps. Step 1, you get your original character code using that ORD function we just talked about. Step 2, you add a fixed number to it, and that number acts as your encryption key. Step 3, boom, you output your new encrypted code. And if you want to decrypt it, you just do the exact reverse. Take the encrypted code and subtract that same key. Let's actually see this in action through a really basic Python experiment. In line 1, we store the Unicode number for the letter D. In line 2, our encryption key is just the number 1, so we add 1 to D's number. Obviously, this gives us the number for the very next letter in the alphabet. And finally, in line 3, we use that CHR function to convert that brand new number back into a letter. We started with D, shifted it by 1, and our final encrypted result is E. Which brings us to section 4, thinking in ones and zeros. Now, that simple shift is a fun start, but strategically, it is way too easy to crack. To really secure our data, we have to think like a machine. And the machine speaks entirely in binary. So the absolute crucial concept here is understanding the bit. A bit is the smallest possible unit of data stored in a computer. Picture your computer as a massive warehouse filled with billions of tiny light bulbs. Each bulb can only be in one of two states. It is either on, which is a 1, or off, which is a 0. Every piece of complex data you own is really just an ocean of these ones and zeros. Section 5. The reversible XOR magic. To build stronger, smarter, and incredibly fast encryption algorithms, we rely on bitwise operations. These are mathematical movements performed directly on those zeros and ones. The undisputed star of this process is the exclusive OR operator. We just call it XOR. In Python, you'll see it written as a little caret symbol. The rule here is incredibly elegant. If you compare two bits and the inputs are exactly the same, so 2 zeros or 2 ones, the result is 0. But if the inputs are different, a 0 and a 1 or a 1 and a 0, the result is 1. That's the XOR rule in a nutshell. It outputs a 1 only when those input bits are different. Now, why should you care about this for your company's security? Because XOR is absolutely perfect for encryption. It is entirely reversible. You take your original message, smash it against an XOR key, and you generate an unreadable encrypted message. But here is the real magic. If you take that newly created ciphertext and you apply the exact same XOR key a second time, it flawlessly spits out your original message. All right, Section 6, unlocking the message. Let's look at how this XOR magic trick actually plays out in runnable Python code. In this example, we're encrypting the character A, and our secret key is going to be the number 10. Look at line 3. The code converts A into its Unicode number, and then it applies the XOR operator, again that's the caret symbol, against our secret key of 10. That mathematical collision creates a completely new number, which we immediately turn back into a character. And just like that, our readable A is securely locked away as ciphertext. Okay, now watch the decryption process. We receive the encrypted ciphertext, which, by the way, turned out to be the letter K. In line 4, we take the number value of that K and we apply the XOR operation against the exact same secret key of 10. Because of the rules of XOR, the math perfectly unwinds itself. Line 5 translates it back into a character, and there it is. Our original letter A is safely recovered. I literally cannot emphasize this foundational concept enough. Applying XOR twice with the same key returns the original value. We call this the reversible property. It is this beautiful mathematical symmetry that makes modern encryption possible. It allows massive enterprise systems to process huge amounts of encrypted data incredibly fast without ever losing a single bit of information. So, we've tracked this strategic growth journey all the way from simple letter shifting right down to the blazing fast binary logic of Python. The math works perfectly every single time. But here is the ultimate strategic takeaway for you as leaders. This entire system relies on one thing: the secret key being exactly the same for both encryption and decryption. The math itself is completely unbreakable, but if a bad actor gets their hands on your key, well, that perfect math works just as flawlessly for them as it does for you. We know the math is secure, so the real question for your organization's future is, who holds your keys? Think about that as you plan your next security initiatives. Thanks so much for joining me on this explainer. I really hope this helps you lock down your success moving forward.